All right, so we've talked about what this statistic is, this value here, 13.5. But we want to kind of figure out what makes it meaningful, or how we decide if it's an important value. And so to do that, we can look at how these statistics are distributed under the null hypothesis. And so here's a histogram of the statistics under the null hypothesis. So what I've done here is I've generated some data under a null hypothesis where n equals 20. And let's be clear here. Let's talk about maybe for a second what I mean by null hypothesis. And so our question here, when we're doing a linear regression model, when we're looking at a specific beta coefficient, for example, here with simple linear regression, we just have a slope for wing length. And what I'm interested in knowing is whether that slope is different from 0. So if that slope was 0, that would mean basically across all of my different x values, it doesn't really matter where I am in terms of wing length. I could end up with basically any value of y. So there's not really a relationship between wing length and weight if that slope is 0. And by slope, I mean this beta hat 1 coefficient. And so I want to determine whether that slope is different from 0. And one way to do this is by looking at this statistic, which basically quantifies the ratio between that estimate or that slope and the standard error. And so it is about 13 standard errors from 0. And so we want to decide, is 13 enough? Kind of, what does that mean? Well, we could look at what it would be under the null hypothesis. And so the null hypothesis is that that slope is 0, so that this beta coefficient is 0. That's my null hypothesis. And if that was true, we would still expect there to be some sampling variability. And so we would expect that if we sampled 116 birds and the true relationship between wing length and weight was 0, we would still kind of see some deviation from 0 just based on sampling error. And so that's what this histogram is here. I've generated some data under a null hypothesis that slope is 0, and equivalently this statistic is 0. And I've seen kind of what values I would expect to see. And so this makes sense here that most of the values fall right at 0, but it's still possible to see small or large values even under this null hypothesis just due to chance. And so here, this null hypothesis here, I'm assuming that n equals 20. And so this is going to be a different shape depending on what my sample size is. But for this one, just for demonstration purposes, I'm assuming that n equals 20, and I'm going to sort of build up to some intuition behind this. And so I can overlay this histogram under the null with a t-distribution to demonstrate that it turns out under the null hypothesis, this is t-distributed. And it's a t-distribution with n minus p minus 1 degrees of freedom, where p is my number of predictors in my model. So in the model that we just fit, where we had an intercept beta 0 and a slope beta 1, and we only had one predictor for wing length, p is going to be 1, and so this would be a t-distribution with n minus 2 degrees of freedom. Okay, so the distribution of test statistics that we would expect given the null hypothesis is true, where the null hypothesis is that beta 1 equals 0, is t-distributed with n minus 2 degrees of freedom. So that's what this looks like. And so kind of intuitively what we're doing here is we're going to compare what we saw, the t-statistic that we observed, to this distribution under the null, and we can figure out how likely it is to see a statistic that we saw. So I've redrawn this here as a histogram of statistics under the null, a t-distribution now with 114 degrees of freedom. And why is it 114 degrees of freedom? That's because I'm using the Sparrows data. And if you recall, in the Sparrows data set, I have 116 observations. And we use a n minus 2 t-distribution, a t-distribution with n minus 2 degrees of freedom because we have one predictor. And it's n minus p minus 1. And so because we have 116 observations, and if we take away 2, so n minus 2, we end up with 114 degrees of freedom. And so that's what this picture is. This is the distribution, a t-distribution with 114 degrees of freedom under the null. And this line here represents what we observed, the t-statistic that we observed at 13.5. And so what we can do is compare basically how often under this null would you expect to see something like this, and whether or not that's likely. Just from this graph, when I look at this, that looks very unlikely. There's very little mass over here. It's very unlikely that you would see something that extreme under the null. And so the way that we actually compare this line to the distribution under the null, well, that's exactly what a p-value is doing. And so the p-value is defined as the probability of getting a statistic as extreme or more extreme than the observed test statistic given the null hypothesis is true. So I'm going to say that one more time because the definition of p-value is really important. It's important to fully understand what this is. It is the probability of getting a statistic as extreme or more extreme than the observed test statistic given the null hypothesis is true. And so we actually look at both sides, two-sided p-values. That's the kind of most common way because we want to assume that either the values could either be on this side, this would be extreme if the values were down here, or on this side, this would equally be extreme. And we're basically going to see how likely it is that you would see something to the right of this line or to the left of this line under this null hypothesis. And that's where this p-value comes in, the 2.62 times 10 to the negative 25th. So this is a very, very small p-value. There's very little mass over here. And I think it's kind of hard to sort of understand exactly what's going on with the p-value with this picture because it's so small. So I'm going to change the example. I'm going to return to some generated data where n equals 20. And so now I'm dealing with a slightly different question. Now I'm showing this is the distribution under the null, where I've got a t distribution here where n is 20. And so in this case, my degrees of freedom would be 18. And I'm saying that I built a new model with different data, and I got a statistic of 1.5 in my sample. And so I can draw a line at 1.5 over my null, and I can see basically how much mass is on either side of this line. So the blue represents values that are as extreme or more extreme than the test statistic I saw, the 1.5 I saw, under the null. And so to calculate this in R, there's a function called PT, which is like the probability T. And you can put in the observed test statistic as well as the degrees of freedom, and it will calculate that probability. And so by default, what this calculates is it looks at the value you gave it, so 1.5, and it looks at everything to the left of this value. It shows you the probability of being to the left of this value. And this is kind of the opposite of what we're looking for. And if you'll notice, it's only one-sided. I don't have both sides. So this is saying that 92%, so this 0.92, 92% of the mass of this distribution is to the left of this 1.5 line. If I use the lower.tail equals false argument in the PT function, I end up with the opposite, so basically 1 minus that. And so now it's telling me the probability of being on this side or on the right side of the line, which is closer to what we're trying to get at. And so this tells me that we have 7%, 7.5% of the mass on this side of the statistic that we observed. And so the thing that we're actually interested in is whether the values are as extreme or more extreme. And it would be just as extreme to be greater than 1.5 as it would to be less than negative 1.5 because this is a symmetric distribution. And so we actually want to know the proportion of area that's greater than 1.5 or less than negative 1.5. And so to do that, we're going to multiply this value by 2. Because this is symmetric, we can do that. And so I'm still going to use my 1.5. I'm going to set my degrees of freedom at 18 because this is a distribution where my sample size is 20. So my degrees of freedom are n minus 2 or 18. I still have lower tail equals false because I'd like to just get this little upper part. and I'm going to multiply it by 2 so that I can get the probability of being on either side. And so I end up with 15%. So what that tells me is that 15% of the mass are as extreme or more extreme than this 1.5 value. So that 0.15, 15, 0.15 is the probability of getting a statistic as extreme or more extreme than my observed test statistic of 1.5, given the null hypothesis is true. So the null hypothesis is, this is a little hypothesis testing, but the null hypothesis here that we're interested in simple linear regression, when we're interested in testing the slope, is that beta 1 equals 0. And the alternative hypothesis is that beta 1 is not equal to 0. And the p-value there is 0.15, meaning that the probability of getting a statistic as extreme or more extreme as 1.5, the observed test statistic, is 0.15, given the null hypothesis is true. So often we have some alpha level cutoff to compare this to. For example, 0.05. That's the most common one. And so since this 0.15 is greater than 0.05, we fail to reject the null hypothesis. Okay, so I want you to use that linear model that you previously fit with MPG and weight using the MT-CARS data. And I want you to calculate the p-value for the coefficient for weight. And then I want you to interpret this value. I want you to write out what the null hypothesis is, what the alternative hypothesis is, and whether you reject the null. All right, go ahead and knit those results and then go on to the next lecture.